time, and the multiplication by powers of 2 also take linear time on digital computer. The things that we have, the main operation that need to be performed with the 4 n by 2 bit multiplications. This Excel, because we broke that term into this. Now those 4 require 4 recursive calls. Okay. Now this is I mean, it's easy to put it in a slide, right? When you go read the book, you're going to spend 2 hours to understand this slide. Okay. Now, so when you do this one, ultimately we're trying to calculate the time, right, to compute n numbers for an input size of n. T is the time, right? So when you have n bit inputs, we get what is known as the recurrence relation. The reason why I just introduced a term here, when I put the notes in the community, you can those things will become a little bit clearer to you. What we are trying to do is, okay, when we keep breaking it down, what is the overall time? How do you calculate that? So that calculation comes to the Tn. 4 came because of the recurrence calls. And what is the Tn by 2? N by 2 meaning at every level, you're breaking the n into 2 parts, right? So to process that each of those parts, you have to calculate. And how many calls we have, like that 4 recursive calls as stated above, that's why it's 4. Plus at the given level, you have to put them all together, the n terms, that is the order of n. Okay. So ON refers to the linear addition of the terms, and the 4 corresponds to the 4 recursive calls, and n by 2 is the division of n into 2 parts. That's what I summarized there. Okay. That is the funny part is we did a multiplication here by resorting to a very esoteric method, right? We split the x term into 2 parts, left and right, and we came up with that formula, right? We did all of those things, but if you really look at it, we still did not get away with the fact that the algorithm is different, but the timing is still the same. Both the methods would still result in essentially order of n squared. Okay, the way we learned multiplication in high school is also order of n squared, by the way. So even though the algorithm here is different, it's the same thing. However, if you apply the trick that I showed in the previous slide, remember I told you the Gauss guy came up with a beautiful idea how we can convert from 4 multiplications to 3 multiplications. All of a sudden the recurrence relation, the time it takes, changes. Instead of 4 times, the coefficient changed from 4 to 3. But if you do the calculations of this, there are some, I mean, if you read the papers, there are some mathematical proofs and detailed calculations that instead of the algorithm being of the order of n squared, n raised to 2, the algorithm now becomes big O, n raised to 1.59. That's almost like cutting 0.5, right? Now imagine cutting 0.5 over at each level of the tree, because when you divide it, you're basically building a big tree. We didn't cover trees yet. Unfortunately, your syllabus is designed in such a way some things come before, and even though some of the foundation has not been laid yet, right? So from going from order of n squared to order of n raised to 1.59, which is, let's round it out to 1.5 or 1.6, makes a huge difference. So this is the essence of this algorithmic analysis, right? How do we always come up with algorithms where the big O always is less and less and less? Okay. Now, if you look at if I have to put it in an algorithm way, what I have done is I explained it to you. Okay, There's a lag here, hold on. Okay. So here is the divide and conquer algorithm in an algorithm pseudocode form that we have learned, right? So input is positive integers x and y in binary. Their product is, right, some n. You say, okay, max size of x, size of y, right? If n equal to 1, return xy, meaning basically if there is a one-digit number, right? There is nothing to divide there. You just return x times y and that's it. But if you have anything more than 1, remember n is the length of the input string. So you make xl and xr, like how I listed there, yl and yr, and then you have to perform the multiplication. And when you do that multiplication, by the way, this you have to follow carefully. It has some bearing on the rest of the slides too. Okay. So you have the P1 where you're multiplying the left digits XL and YL, right? Those are the leftmost. And then you're doing the right digits, multiplying XR and YR. Okay. Remember you had the then you have the other remaining terms there, right? That's why you get P3, which is multiply XL plus XR and YL plus YR. Okay. When you do that, then you have the last step where you're returning a value, some equation that comes there. Again, these equations are coming out of the example that I gave you there. For you to understand those equations, as I told you, it will take time. I cannot spend the next 1.5 hours explaining that term, right? But that is what it is. You have to convince yourself, right? You have to do a little bit of reading and then you return that. Now these 3 terms that I listed here, there's a meaning to those 3 terms. That is what we will cover, okay, as we go along. Okay, so what we did there was, for that algorithm, you should do the analysis. That recursion that happens when you keep dividing until what time you divide, as I told you, when the subproblem size gets to 1, size 1. Okay. Now, when you do a division, we'll actually draw the tree. Okay, in a second, I'll show that to you. The height of the tree. What is the height of the tree? Meaning, you put it back to how far depth, how in depth you would keep dividing. Right. So if you have, for example, let us say 4. If the input size is 4. So you divide once, then each set would have two elements, right? So at the root node you had 4. At the next level you have 2 elements each, right? And then you divide again 2 elements each. Then you go to 1 element each and you stop. So you just built a height of 3 there, or 2 rather, right? Root node, first level, second level, 2. Okay. And then the branching factor, as we call, is when you branch those three subproblems that the 3 what do we call it? The 3 lines that I showed you here. The 3 corresponds to these 3 statements there. That is the branching factor. Okay. Now, typically at depth k in the tree, there are 3k subproblems. Okay, 3 raised to k. When I say 3k, you mean 3 raised to k. I'm using the term 3k loosely, but it's 3 raised to k. Each of size n by 2k. Now, I don't see your faces, but I can tell you that half the students would be totally lost with the blank eyes right now. Okay, because these are the kind of things where you literally have to sit down, you have to take a sample data, put it on a piece of paper, yourself, draw it, like how I do it whenever I teach this class or whenever I do my other analysis work. That's how you convince yourself. And we do have examples to show you that. Okay. Now, when you do these things, then for each subproblem, you do a linear amount of work, right? Because you have to first divide, right? You have to identify further subproblems and you have to combine the answers. So researchers who have produced papers, they have come up with this depth. The total time spent at any depth k in the tree is 3 raised to k, and then order of this n over 2 raised to k. You simplify that, then it becomes what this shows here. Okay. Now when k equal to 0, meaning the depth k is depth, right? 0 means of the order of n, meaning there's nothing to divide. So remember, that is the size 1 type of a thing. Okay. Now when the depth is log 2 raised to n, right, then it becomes order of 3 log 2n, which again can be written as order of n log 2 log 3 to the base 2, like that. Okay. A lot of mathematics there. I'll give you some practice problems too, by the way, for you to apply these concepts. Let me pause here for a second. Okay, let's take an example maybe. Okay, so I'll create a new slide here. Let me draw a table. Let's assume I'm just taking one thing here, right? X. So when you want to keep dividing this set, I'm not taking the multiplication itself. I'm just here. I want one, right? If I divide this one in the next level, divide by 2, right? So in the next level, what would I get? If I have to draw another table here, I get 4 here, right? I get 1, 0, 1, 1, okay? And then I can copy paste that one. I get, I'm not able to move, okay? I get 0, 0, 1, 1, okay? Now you want to divide the 1, 0, 1, 1 into 2 again, okay? So when we do that, we are going to get 2 element, right? So I'm going to get 2 elements here. And then I'll say Control C, Control V, Control V, Control V. You can see the tree, how it is being built, right? So you will see the depth, how we are getting it. 1. These are all legitimate questions, by the way. In a midterm, when I give you something like this, or your professors give you something like this, they can show you, they'll ask you the depth of the tree and all that. So what do I get here? I get 1, 0. Sorry. I get 1, 1. I get 0, 0. If you have any questions, please put it in chat. I'm monitoring the chat here. Since they are muted, then I can expand. Okay. And then the last one. The last one would be, for sake of completeness, let me finish that. Okay. Now let's say 1 column. right? Okay. So you get 1, and then I'll just copy paste a few of them. Sorry, I did something there. So I'm just putting one sample data there, and then you have 8 of them, right? So what is the what did you say the depth of the tree would be? Log 2n, right? If you go back to the previous slide here, it says log 2n. Log 2n in this case would be 3, correct? So this is level 1, level 2, level 3. Okay. So at each level, that is what it is showing here, right? So at depth k, there are 3 raised to k subproblems. Okay, each of size n by 2k. So you can convince yourself k is equal to 3 and 8 by 2 raised to 3, kind of like that. Okay. Okay. Now, where do we apply this thing, right? Why is divide and conquer so useful in computer science? Here is a classic example, right? Everyone does, as my friend and professor put it at UT Austin once, he said, life is all about sorting and searching. If you become good in sorting and searching, that is 80% of the battle. Okay. Good sorting, good searching will get you a lot of places. So here is a binary search example. Okay, what are we doing in a binary search, right? The goal is to find a key in a large file. So I give you a very large file in some sorted order, okay, and you want to search for it. Right? I do not know if you have written the search programs in your computer science class or not, but if you did, you would know that. Okay. Now, what is the order, the recurrence for that? Okay. Basically, there's a formula here based on the depth. I think I mistyped something here. I'll correct it and put it in the notes. But the running time for searching for an element in a sorted array like that using binary searches, log n. Is log n better than, let's say, n? Obviously, yes, right? Remember I showed you the table last time that the running time when you go from left to right, I gave you that cheat sheet last time, and I think it was the last slide, I think. It's better to always achieve log n times. That is probably the best, one of the very best. Okay, so that is why we use binary search. Okay, let me pause here. Any questions, comments? Let me open the thing here for questions and comments. Type in your questions if you have any, and I'll just get a cup of water here. Give me a second. Binary search is one of the important algorithms that we have in computer science, because the search, remember in the beginning of the term, I made you execute the sorting algorithms and all that. We did a little bit of analysis. We said if you do a simple or a simple search, the order would be, if you do a linear search, the worst case is what? Order of n, right? So this, by reducing it from n to log n, you would save significant time. Okay. Okay. I'll give you a 5-minute break in a couple of minutes, or 5-10 minutes. Okay. Now, the other things where earlier is in sorting. There are two sorts which are pretty famous in the literature, as opposed to the other sort like insertion sort and selection sort and all that, right? One is the merge sort and the other one is the quicksort. Okay. So what is a merge sort? Okay. So you're basically taking an input sequence S, right, which has some n elements. You're going to partition that. So you're going to partition that input sequence into two sequences. And when you partition it, you are applying your divide and conquer strategy there. Okay. So you're going to recursively sort S1 and set S2. That means you take S1, you again recursively, you divide that again by 2, right? And then at the end, you combine those two, merge both S1 and S2 into unique sorted sequence. That is the merge sort. Okay. You probably have written in a code in your programming, and then I asked you to practice that. I said, hey, go implement these things and get some refresher, right? But in terms of an algorithm, in case I have to, if I ask a question, hey, show an algorithm for merge sort in a test, this is how it looks like. Okay. So your merge sort, you have an array, you get an output which is sorted. And if it's n greater than 1, you continue to divide, right? You return the value of the merge. See, that is a recursive function, right? You probably would have written a recursive function in programming, like for example, like factorial. I think factorial, when you do the n factorial, you write recursion. And I think even Fibonacci sequence also, you write recursion, if I'm not mistaken. Okay. Now, again, if you look at the timing factor of that, right? It's of the order of basically n log n. Now, how do you arrive at those things? At each level of the divide and conquer, you get that first factor 2t at each level, right? 2 times 2t n by 2. N by 2 is the you're breaking it down into two parts, right? At each level, so you get 2 n by 2, 2t n by 2 plus at each level you have to put them back together too. So that is the order of n, that linear. So if you add those two things mathematically in the big O notation that we talked about, it comes to n log n. Okay. Now I'm showing you the timing efficiencies of these algorithms like that. But you might ask me the question, how to come up with these formula like that, right? You don't come up with this formula just like out of thin air, right? It is very hard. It takes a lot of effort to generalize a formula, right? So if you were my student, I would not, I mean, in the sense like you would take my tests, and the way I grade my students, I never try to tell them, okay, tell me what exactly is the formula. No one remembers these formulas, but general ideas, right? You say, hey, quicksort and merge sort are better than the brute force sort, right? That's the kind of thing that I expect them to remember. But if I give you a program, remember last class, I showed you a lot of programming examples. And for each programming examples, we discussed the concept of the primitive operations, right? So I would certainly test the students' knowledge in terms of coming up with some formula based on the primitive operations that the program performs. Okay. Whatever programming logic is, as opposed to asking you, hey, what is the formula for merge sort algorithm? I'll give you real programming example of how the merge sort is working. Okay. So you have the input 10, 2, 5, 3, and all of those things. So you can see how it is broken down, right, into the respective numbers there. And then how in the tree there, you are coalescing those numbers at the bottom of the tree. It's kind of like a bottom-up tree, right? 10, 2, 5, 3, 7, 3, 1, 6. Those are all the what I would call it as like the root or the branches, right? leaves of the tree actually. So you put them together. That is how the algorithm works visually. I'm not going through each and every step of the merge sort. I already made you write these algorithms right in the beginning itself. Okay. How many of you can write a merge sort algorithm on the fly? If I were to say that, hey, you have 1 hour to write a merge sort algorithm, code it and do it without looking at the book, how many of you think you can do that? Show of hands. I'm looking at Chaitanya there. Without looking at a book, do you think you can write a merge sort algorithm? If anyone can write, they can put it in chat. If JNTUV students say that, your faculty member can put it in chat. You can do that. Okay. Writing algorithms is not easy, but they are general, right? The idea is to know how to calculate these big O's, right? Small O, omega, theta, which we covered in the last chapter, and then basically they use those concepts to arrive at these numbers. Okay. Okay, JNTU Kakinada, they can write it. Perfect. Okay. Let me. Now, what is Quicksort? Okay, that is another famous sort, right? Quicksort and merge sort are the two famous sort algorithms, right? I think I mentioned to you this was given to us by Tony Hoare, very famous man, still working as a professor in one of the English universities, right? The essence of Quicksort is you're given some kind of a random array, right? You pick an element, you call it a pivot, right? We use that concept of pivot in Excel spreadsheets quite often. And then you partition the array based on the pivot. So how do you partition it? There's a logic to it, right? You reorder the array in a way where all the values that are less than the pivot come before the pivot, but all the things that are greater than the pivot will come into another array. Okay. Okay. Now, after you do that partition, the pivot would be in its final position. That is why it's called the partition operation. Now, if you read the literature on this one, coming up with the pivot and partitioning, right? There are so many different authors who tell you how to choose a pivot. There are certain algorithms where they choose the last element of the array as a pivot. Okay, and there are some which choose the first element of the array as a pivot. Tony Hoare does it in a different way. Okay, so how you do that has something to do with call it as the algorithmic efficiency. Okay, but in general, I'm not going to go into those details, right? There's a lot of research that goes on in this. In general, when you do Quicksort, it is considered like, I think, pretty much one of the very fastest algorithms to sort. Okay. If you notice, I left the slide blank here. So what I want you to do here as a take-home exercise, right? Sorry. This one student there are I think 220 students who signed in the community. In this topic, I'm going to start a discussion topic there. And in the topic, this is what I want the students to participate actively in the discussion, right? So I want somebody to explain pivot concept. Okay. I want someone explain when you would use Quicksort versus merge sort. Okay, that is one discussion topic that I'm going to put. And then the third one is what is TN for Quicksort? Okay. Take a sample data set of less than 10 elements. And compute the order. Okay. Using the concepts of primitive operations that we considered. Okay. You all understand what the assignment is? If you do that, then you would do your midterm very well. The questions would be exactly like that. I don't know if your professors usually tell you how the midterm is designed there. Would it come as a surprise or not? But okay, somebody said you can write. Excellent. Excellent. So the guy who said he can write, please do write and put it in the community. Okay, without looking at the book, it's an honor system, right? Okay. Let me pause here. My usual tea break of 5 minutes. Class is silent. Let me unmute JNTU. Somebody, I'm just picking at random here. JNTUV, how are you? Hello. Questions, comments? And conquerors. We'll be doing a lot of these examples, by the way, on this throughout the semester. I just gave you an introduction there because once I introduce you to tree structures and so on, you will implement some of these algorithms more thoroughly. JNTV, any questions? Oh, you people don't have any questions. That means you understand. Okay. I'm assuming you have downloaded my slides from last class. I've already posted the lecture notes there. I'll post this also. Take a 5-minute break here. Stretch break. Please get up, stretch yourselves. I'll go get my cup of tea and then we'll continue. Okay. Time now is 10:18. I'll be back at 10:18 and make a time in the 5 minutes. Okay. Can you? Okay, guys, good. I'm back. I'm sure you took the 5 minutes to call your girlfriends, boyfriends, or moms, dads on the cell phone. I always need my tea when I'm teaching my class, right? Okay, so I'm sharing with you an example here. Yeah, hold on, guys. I need to close the door. I have 4 kids and wife upstairs who are saying, close my door here. They're all busy studying. Okay, so I'm showing you an example, how this looks like. Okay, again, my dog opened the door. Hold on. Tiger, hold on. So here is a piece of code for doing that divide and conquer search, right? Binary search. You can see here, pretty straightforward how you can write that code. Again, I'm not going to go into the details of it, but you can see there's a piece of code here in case you want to execute it. Okay. Basically, one thing to note here is you're always looking at low plus I divide by 2. That is what it is, right? Binary means you're dividing it into 2, basically. Okay, pretty efficient piece of code there. Here is a visualization of the search, binary search. Okay, so you have a low, you have a high, you divide it, you're getting a midpoint. Okay, and then you have a key value. Remember, I talked about a key value, right? Then again, you apply the low high. That is how it proceeds. Okay. Goes back again. I gave you the formula at the beginning, right, of the section as to the depth of the tree and so on. Depending on the number of elements, it's log 2n. That is the depth. And then it's cases. Okay. I don't have to tell you about all these things, but that kind of gives you some kind of an idea of a binary search. And when you talk about recursion again, I mean, this is all recursion, right? Whether you do binary search or whether you do other types of recursion like linear recursion, where you're adding here, in this case, you're doing an addition, right? So it shows you some examples of how the recursion happens really. For those of you who want to drop the recursion. Okay. Some examples there. I'll just put it there. I'm not going to go through each of these things. I'm just showing you how you do that recursion. When you are doing all these divide and conquer approaches, there's an element of recursion. So how do you set the recursion? In case you've forgotten, this slide should help you get back to that. Okay. So let me switch gears here. When you're doing these things, what you're doing basically is you're building trees, right? So what exactly are trees? Have you learned the concept of trees in any of your programming languages before? Somebody can put it in chat. Any language, any class that taught you trees? Where is my chat here? Okay. From SVECW to everyone, you said yes, sir. Yes, sir, meaning for trees, I assume, right? So I'm going to put it in full screen mode. Give me a second. I'll put it in presentation. Okay, I put it in presentation mode there. Okay, I'll do a quick review of that. See, what happens is, right, one of the things is that we all understand tree is a hierarchy, right? So there are different types of trees and all that. So let's do of trees here. If somebody has not really covered this, if most of the colleges didn't cover this, I'll be very happy to do a formal class on that. Couple of quick concepts here for algorithms, right? One thing students you should note here is, right, there is no spoon feeding or anything like that here. These are all different concepts. I expect you to do a lot of reading on your own too. Right, and then we use the community where you ask questions and I answer them. So it's like a classic approach of you ask and I give, right? Okay. A couple of concepts here. Multiway search tree. What is that? It's an ordered tree. Okay. Now, do you know what an ordered tree means? Who wants to tell me what an ordered tree is? What is an ordered tree? In general, when you say a tree, when a tree is ordered, what do we mean by that? Faculty members are welcome to comment too. What is an ordered tree? Tree is a hierarchy, we know that, right? You have a root and then you go down levels, right? And then you have the left side and then the right side. Okay. And then each of them ultimately have leaves. Okay. So a tree can be unordered or ordered. So the question is, what is an ordered tree, right? Anyone can put it in the chat here if you know that. Or think about it. That's a question that you have to think about it, okay? Those are the concepts. So when you have a search tree, okay, so you can see some definitions of these trees here, because when you do the divide and conquer algorithms, you're applying those things on these tree structures here, right? So each of the nodes has at least 2 children, okay? And then it stores some key element items there, right? Where it has number of children for each node, okay? So whenever you have when you have a node with children v1, v2, and then each of them are saving keys, right? So keys in the subtree of v1 are less than k1, vi are between k and so on. So what it basically means is that depending on when you're traversing the tree and when you're reading those numbers back, they're always in sorted order. When you have an ordered tree, the numbers, when you're traversing the tree to display the items, I don't know if you have written a tree traversal algorithm. Okay, so for each node you go to the left, and then if there's for that left node again it has branches, you go down. So there's a tree traversal algorithm that you write. So whenever you're doing divide and conquering, you're using the concept of tree to sort those things. And then to display them back, you need to know the traversal of the trees. Okay, so an ordered tree would let you get to yes, each node having 2 children, correct. Good job, Jntuk. Okay, so you can see an example there, right? Okay. So there are different types of traversal. There's something called Inorder traversal. Okay. You can see here how you're doing an Inorder traversal, right? Where it visits the keys in increasing order. Okay. So this shows how to search, right? Similar to search in a binary tree, right? So it gives you an algorithm there, okay? And you're searching for 30 there. It gives you the algorithm how you go through each of the key values there. And once the value is found, then of course you stop. Okay. Again, I'm not going to the full details there. Okay. So here is another type of tree here. Okay, 2-4 tree or 2-3-4 tree. It's a multi-way search with the following properties, right? So these are all kind of like a little bit advanced concepts. Now, all of you are telling me you have done trees. That's why I'm kind of going through that fast for now. But we'll come back to it when we implement some algorithms on the trees, okay? So look up what a T43, right? Okay, theorem. The moment I see the word theorem, I usually delete it. Okay. So how do you insert a new item at the parent V of the leaf reach by searching for K? Okay. So these are all some of the, like for example, programming, have you learned something like Stack Overflow and things like that? Simple examples. I'll give a simple example, right? You have done like a C programming, right? Basics of C. When you declare an array in C, you all know that in C, you have to do array bounds, correct? Array bounds check. C does not as a language give you bounds check. If you don't do array bounds check, if the elements of the array, let's say you declare 100 element array, okay, I can write a statement where I can say some variable name 101 equal to 20. The the compiler would not complain about that at all in C. That's an overflow. Okay, so you have to deal with those kinds of situations too. Okay, so how do you deal with overflows in trees? Okay, you can see here the way you handle those things is by splitting. Okay, it's easy to say that pictorially. How you do that programmatically is what your challenge is, right? Not my challenge. Okay. And then there's some analysis that you have to do there. I will not go into that, but I just want to give some basics of trees there. So basically, when you have trees, you go through the concept of a root, and then you break it down, and then they have children. Ultimately, you get to the leaf level, and then when you build a tree like that, you should know how to traverse the tree. Traverse meaning navigating the tree. There are different types of traversals. One of the cool things that we do is the Inorder traversal. Okay, you need to understand that. Now, what binary trees are? They're a special subset, right? When you say binary tree, what does a binary mean? Binary tree means 2. Always has 2 children. Every node, and I'm just putting it chat 2. Every node has. I'll just put one statement here. I want to ask if that is a true statement or not. Every node has 2 children. Is that a complete statement? Chakravarti, you can correct me on that. In a binary tree, does every node has at most 2? Correct. I think it's not only at most, it is like 0 or 2, right? Shouldn't it be 0 or 2? It's either 0 or 2. It cannot be 1, I think. Am I stating it correctly or am I stating it incorrectly? Some of the faculty members can help me out here. I think it's when you say at most, it has to be. So there's so much for the tree there. Questions, comments? Okay, so what I want the 1 second. Cancel. What? Please let me know when you see my screen. You should be seeing my screen now. Okay. So that was, since you kind of, most of you said you kind of know the trees. What about queues? Do you know queues? Algorithms and data structures go together. Remember that, right? So brief overview of queues here in the remaining time. Okay. So whenever you have a queue, it's an abstract data type, right? When you say an abstract data type, what you mean is you don't have it's in the syntax of the programming language. You have to implement that using some of the primitive data structures, right? So when you have a queue, lot of applications of queues, right? For example, your fundamentals of operating system class would have taught you how the CPU takes it from a dispatch queue, all the tasks from a dispatch queue, and executes them. Okay, so you have insertions and deletions also, and then most of the queue data structure, it's always first in first out scheme, right? So you insert at the end, and then you remove it from the front. So you have these main queue operations called NQ and DQ, right? So and then here are the 1 second, did I miss something there? Yeah. Okay, and then you have other operations too, right? Other operations, like the first, what is the first element of the queue? Okay, let me ask a question when I'm talking about it. Give me one example, put it in chat while I'm lecturing here. Give me an example. Somebody, before I go there. Okay, Jntuk Kakinada said that, yeah, a binary tree can have one child also, correct? Okay, if all nodes except the leaf nodes have two children, then it's called a complete binary tree, correct? I'll put it for the benefit of everyone, right? Okay, so you have a binary tree versus a complete binary tree. Okay, so that's when everything has two children, then it's a complete binary tree, except the leaf, of course. Okay, thank you. So when you talk about queues, right? So you have the concept of NQ, DQ, and then you can always do operational first size of the queue is the QMT. These are all the things that you write in terms of algorithms, right? While I'm doing this, somebody put an example. Put an example of queue. Where would you use the concept of a queue data structure? Okay. Before I go there, there are some examples which I can do. Oh, there you go. Before you answered, probably I already answered, right? So wherever you have waitlist, I don't know what it means by bureaucracy, waitlist, right? We always have waitlist whenever we write programs, correct? Whether it is operating systems, whether it is distributed control, shared access to resources, right? Multi-programming, multi-user programming, internet, everything, all in today's world, queues are everywhere, right? And then you can build a hierarchy of queues too, by the way. Like you have priority queues. Remember, in operating systems, you'd have learned about priority queues and then multi-tier queues. So you can use these data structures there too. Now, how do you implement a queue? Here is one example, right? You can implement a queue based on arrays. Okay, and then pretty standard stuff. You have the front of the queue when you implement it as an array. Then when you have to write an algorithm here, this is, by the way, legitimate, okay? When I say in an algorithms class, a legitimate question to ask you, hey, I have a queue and I would like you to tell me how you'd implement an array. And then when you implement an array, how would you navigate that queue, right? Very legitimate question. So what are the variables that you need to keep track of, right? And then both front and the rear, right? Because you cannot go beyond the array limits, right? That is the reason why it is a circular queue. What a circular queue means is when you go to the end, you rewrite. You go back to the first element and then you rewrite, overwrite that one. Okay. And then how do you always keep track of the first empty slot? Past the rear queue. That's what this is showing you there. Okay. So what is the algorithm size, right? That's shows nothing great there. So here is a NQ. How do you put the element in the queue, right? So when I ask you these questions, there's nothing to memorize really there, right? As long as you know that, hey, it's an array, it's common sense, right? Even on a piece of paper, you can come up with an algorithm on the fly. There's nothing to memorize there. But the concept is okay. If I'm implementing a queue, the concepts are front of the queue, back of the queue, I insert, delete, right? And it's first in, first out. If I know those concepts, then I can implement the array like how this slide is showing you. Okay. Now in your C++ class, you would have learned about how to catch and throw exceptions, right? So when at least here, when we ask the students to write algorithm, these are the kind of things which would distinguish a grade student from not a grade student. Let me put it that way, right? So you have to look at the exceptions too. Whenever you're writing algorithms there, you have to look at the exceptions. That's what this is showing you there. Okay. I'll not get into the Java there. I kind of, okay. But here is some code for you in case you want to implement some of these things. The code is available to you. Okay. Chakravarti, let me ask a question. This is a question for him. It's a core class. Can the guys do a project or not in our class? Does your core curriculum allow for students to do projects together or not? Because some of these things that I'm showing, I'm expecting the students to do a project where they can implement these things. Okay. Okay, somebody here commented saying online reservation of everything, train, bus, etc. is the queue. Yes, I agree. Okay. Okay, here are some examples of queues that are showing you round robin queue, which we talked about. Okay. Any questions, comments on that?